The final part in this session is the partial wave equation. The purpose of Chapter 5 and Chapter 6 is to find out the diffraction field amplitude U. For this problem, at the initial point, we have known the amplitude is U0, and the purpose for Chapter 5 and Chapter 6 is that how could you find out the diffraction amplitude U at any value of Z. Okay? Our purpose is to find out the diffraction amplitude U at the arbitrary value of Z. In Chapter 5, we have learned that the whole problem can be considered as a diffraction system. So to find out the value of U, to find out the diffraction amplitude U, you can use the impulse response of this system. What is the impulse response of the diffraction system? That is the H function. Okay, so the diffraction system can be considered like this, with the impulse response H. So if you know the input amplitude, the initial amplitude U0, you can obtain the diffraction amplitude U by the convolution of U0 and the H function. That is how we find out the diffraction amplitude U in Chapter 5. How can we find out the same result in Chapter 6? In Chapter 6, we find out the diffraction amplitude by find out the characteristic equation of this system. For the same diffraction system, in Chapter 6, we try to find out the characteristic equation of this system. Besides, we also want to find out the corresponding solutions. Suppose that the corresponding solutions for the characteristic equation of the diffraction system is x1, x2, and xn. Then we say that the initial amplitude U0 can be expanded by these solutions. What I am saying is that the U0 can be expressed as the superposition of these solutions. So U0 can be written as A1x1 plus A2x2 plus A3x3 and ANxn. Okay? Where A1, A2, and AN is the corresponding weighting factor. And if you know the diffraction field of each solution, what I am saying is that if you know x1 and you also know the differential field of x1, which is f of x1, you know x2, you also know the differential amplitude of x2, which is f of x2, and you know xn and the diffraction amplitude of Sn, which is f of Sn. If all above are known for you, then the diffraction amplitude of the u0, which is u, can be written as a1 of a1 times f of x1 plus a2 times f of x2 and plus an times f of xn. What I'm saying is that the diffraction amplitude u is also a superposition of the diffraction amplitude of these solutions with the same parameters shown here. Okay? But what is the characteristic equation of the diffraction system, and what will be the corresponding solutions? We will talk it later. Okay, in this slide, I will try to derive the characteristic equations for the diffraction system, that is, the Paraschier wave equation. Let's consider the wave equation. We have learned that the wave equation can be expressed as Laplacian phi minus the inverse of c squared times partial square phi over partial t squared, which is 0. And of course, we can transform the wave equation into the phasor form to have the Helmholtz equation. And the Helmholtz equation gives us Laplacian phi plus k squared phi is 0. Here phi is the phasor of the phi function in time domain. Okay, and you should know that the k squared should be omega squared times mu epsilon. Suppose that you should be familiar with this Helmholtz equation. Could you tell me what will be the solutions of the Helmholtz equation? We all know that the solution of the Helmholtz equation is phi should be the amplitude u times exponential minus jkz. Okay? Because we express it in a Paraschier wave form. And I have told you, in this situation, this term is a slow varying term, and this term is a fast varying term. This term, the amplitude term, will change slowly, and this term, the exponential minus jkz, will change very fast. And then, let's go back to the Helmholtz equation. The Helmholtz equation gives us Laplacian phi plus k squared phi, and for the left hand side here, we can rewrite it as Laplacian t transverse Laplacian plus partial square over partial z square plus k square phi is 0. Compare these two sides, you can clearly know that Laplacian here is replaced by transverse Laplacian and partial square over partial z square. Okay, so Laplacian can be re-expressed as this one. And of course, this term is partial square partial x square plus partial square partial y square. Okay? The following step is take the expression of phi into this Helmholtz equation. What we will deal with is what is the result for partial square phi over partial z square. So let's see it. For the phi function is the amplitude function u times exponential minus jkz. Let's perform the operation let partial phi over partial z. Clearly, according to the result, the expression of phi shown here, which u is a function of z and the exponential is also a function of z. So partial phi over partial z can be obtained as the following equation. Okay? As you obtain the result for partial phi over partial z, let's take the partial over partial z of this equation again. What I am saying is that let's perform partial square phi over partial z square. According to the result shown here, this operation will give us the following terms. Okay, according to the result I have derived here, let's rearrange the equation, the Helmholtz equation. The above Helmholtz equation can then be written as the transverse Laplacian of phi function plus the result shown here, it is the following terms. Okay, and clearly you see that this term can be cancelled by this term. So the above result can be rewritten as Laplacian, transverse Laplacian u plus partial square u over partial z square minus 2jk times partial u over partial z is 0. And as I have mentioned that the expression in the phi function shown here, we have a slow varying terms u and a fast varying terms exponential minus jkz. So for the absolute value of partial u over partial z, this one should be very small to very smaller, much smaller than k times u. Because for the term u is changed very slowly compare with respect to the z. So if you perform partial u over partial z, you will obtain a very small value. So we have this condition. Then you can also say that the absolute value of the partial square u over partial z square will also be much smaller than k times the absolute value of partial u over partial z. Okay? This result is obtained by perform partial over partial z of this equation. According to this result, you see, we have this term shown here. We have this term shown here because compared to this one is very small. So this part can be ignored. Then, for partial propagation, we then obtain the partial wave equation. Which give us that transverse Laplacian u minus 2jk partial u over partial z is 0. So you can find out the value of u by solving this partial wave equation. Okay? So let me summarize what I have told you. We have started from the wave equation, and in the phasor form, the wave equation becomes the Helmholtz equation. And we know that the solution for the Helmholtz equation should be a point source. Point source solution, which can be written as exponential minus jkr over r. If r is very large, this term will become a plane wave, okay? And for partial approximation, the phi can be expressed as u times exponential minus jkz. Then, let us perform the partial approximation. In the derivation of the previous slide, you know that the wave equation after partial approximation, it will become the transverse Laplacian u minus 2jk partial u over partial z is 0. And then what will be the corresponding solutions? To find out the corresponding solutions, we can just perform the partial approximation of the original solution. Okay, so consider the original solution shown here. We know that the position r can be expressed as the square root of s squared plus y squared plus z squared, which can also be written as z times the following term. Okay, and as the wave propagates very far away from the original point, z will be very large compared to x and y. So this term will be much smaller than 1. As a result, this term can then be approximated as 1 minus 1 plus half z square x square plus y square divided by z square. Okay, and take the value z into these two terms, you will have z plus x square plus y square over 2z. After we have obtained the approximation value of r, take this result back into the original solution. Then, exponential minus jkr over r can be written as, can be approximated as exponential minus jkz times exponential minus jk x squared plus y squared over 2z. And here, because z is very large, r can be approximated as z. And I have said, under Paraschier approximation, the field can be written in this form. So, compare with these two. You can find the common term shown here, right? So, it will give us that the u should be exponential minus jk x squared plus y squared over 2z divided by z. Okay, which can also be written as that the u should be in proportion to the inverse of z times exponential minus j k over 2z times x squared plus y squared. Okay, as you obtain the result shown here, if you remember the h function, what is h function? H function is the impulse response of the diffraction system, right? And we know that h function can be expressed as this one. Compare the h function and the result shown here. We can have the conclusion that the solution of the Paraschier wave equation u should be in proportion to the impulse response h. Okay? Let me say it again. Under the Paraschier approximation, the wave equation can be approximated as this one, and the corresponding solution of this characteristic equation should be u, which is in proportion to the h function, and the h is the impulse response of the diffraction system. We then will discuss in detail the form of the h function in Chapter 6.